The paper addresses the issue of missing values in tabular data, a ubiquitous problem across industries, and proposes an advanced diffusion model called Self-Supervised Imputation Diffusion Model, SimpDM. It identifies two key mismatches: objective mismatch and data scale mismatch, that hinder the performance of existing deep generative models in imputation tasks. SimpDM integrates self-supervised learning techniques into tabular diffusion models, introducing a self-supervised alignment mechanism to provide consistent and accurate imputation. The model also uses state-dependent augmentation, a perturbation-based data augmentation strategy that improves the robustness of the diffusion model. The paper reviews related research directions, including tabular missing data imputation in diffusion models, highlighting the competitive performance of generative model-based approaches. SimpDM utilizes a simple MLP architecture with learnable embedding of diffusion steps and missing mask as input conditions to discern the status of the hybrid input. The pseudomissing training strategy is employed, involving padding missing entries with column-wise average values during training, sampling pseudomissing masks, and adding Gaussian noise to entries where the condition mask equals 1. The value prediction and loss calculation processes are discussed, where the model directly predicts the missing values and calculates the loss on pseudomissing terms. The training process of the Gaussian diffusion model for tabular data imputation is expressed, focusing on the pseudomissing terms to guide the model towards completing the missing data. The paper demonstrates the potential of diffusion models in tabular data imputation tasks, providing a comprehensive methodology for enhancing these models through self-supervision. Here is a combined summary of pages 58. The authors propose SimpDM, a novel diffusion model for tabular data imputation that addresses the limitations of existing methods. SimpDM introduces a self-supervised alignment mechanism to suppress the sensitivity of diffusion models to diverse noisy inputs. This mechanism involves constructing two parallel channels with shared pseudo-masks and condition masks, sampling different diffusion steps and noises, and minimizing the difference between the outputs of the two channels with a self-supervised alignment loss. Additionally, SimpDM employs a state-dependent data augmentation strategy, which perturbs entries in different states with varying strengths, generating more reliable training samples and boosting the robustness of the diffusion model. SimpDM is extended to handle mixed-type data by introducing multinomial diffusion processes for categorical features and using random state transformation as perturbation. The authors evaluate SimpDM's performance on 17 real-world datasets across various domains, comparing it with 11 baseline methods, including shallow, deep, and deep generative methods. Experimental results show that SimpDM outperforms all baseline methods in terms of root mean squared error, RMSE, achieving an average rank of 1.4. Ablation studies demonstrate the effectiveness of the self-supervised alignment mechanism and state-dependent augmentation strategy, with the mean squared error, MSE, loss attaining optimal results on 7 out of 8 datasets. The training time of SimpDM exhibits a linear relationship with both the number of samples and the number of dimensions, aligning with the author's analysis. A case study and visualization experiments illustrate that SimpDM yields increased stability and enhanced accuracy, capturing the data manifold effectively. Here is the combined summary of pages 9 and 10. SimpDM, a self-supervised diffusion model, is proposed for tabular data imputation, aiming to mitigate noise sensitivity and enhance imputation stability. The training procedure involves sampling a pseudo-mask, running the diffusion model on 2 channels, and calculating the self-supervised alignment loss. During inference, the input is initialized with random Gaussian noise, and the denoising iteration is recursively applied using the diffusion model. The time complexity of SimpDM is analyzed, revealing a linear scaling with both sample size and dimensionality. The model is evaluated on 17 datasets from the UCI Machine Learning Repository and Kaggle, with dataset statistics provided. A comprehensive review of related work in diffusion models, imputation, and synthetic data generation is presented. This review encompasses topics such as personalized risk scoring, finance-related synthetic data generation, the UCI Machine Learning Repository, perturbation learning, contrastive learning, and denoising diffusion probabilistic models. The authors highlight their contributions, including the development of a self-supervised alignment mechanism and a state-dependent augmentation strategy. They also acknowledge limitations, including the need to explore more complex self-supervised alignment losses and apply SimpDM to more challenging datasets, which are identified as potential avenues for future research.